Okay, so I just had a bunch of stuff get deleted, so I'm kind of angry. I'm going to go through these slides kind of quickly because, again, I just recorded them and then stuff happened. Okay, so where we had left off. So we had light, right? So we had shown that for the most part, light behaves like a wave. We had shown that with our little video, so you should watch that video if you didn't. On the other hand, though, we can't explain all of the behaviors of light in terms of wave-like properties. We also have to kind of invoke a particle-like nature. So particle-like nature when it comes to energy, right? So Einstein had shown that the energy of light is proportional to its frequency, right? So energy is proportional to the frequency. Has nothing to do with the amplitude, which would be very much wave-like. And so this energy is kind of delivered in little packets that he called photons or quanta, okay? Okay, so we'd also talked about matter. We kind of briefly talked about matter with respect to emission spectrums. So emission spectra of various elements, right? So with emission spectra, if you go and excite an element, either via like electrical excitation or heat, they tend to give off these very characteristic colors. They tend to glow these very characteristic colors. And then when you take that color that they're glowing, you pass it through something called a spectroscope. It essentially kind of takes out all the various components or factors out the various components of that color, and you get what's called an emission spectra, right? And so these emission spectra are very discrete spectra, right? So there are just essentially patches of black with very sharp discrete lines at very specific wavelengths. And again, these emission spectra are characteristic of the element that are producing them, right? So the emission spectra for hydrogen, especially in the ultraviolet visible region, is like 4 lines, right? And so if you were to take hydrogen from any source and you were to do the exact same thing, excite it, past the light that it's glowing through a spectroscope, you would always get this exact same 4 sharp line emission spectra, okay? All right, so then we talked kind of briefly about how the student named Rydberg had modeled the hydrogen emission spectra, but he hadn't been able to explain why his model worked. And then we were left with this guy named Niels Bohr. All right, and so Bohr had attempted to explain what we are seeing with respect to this idea, this Bohr model of the atom, where we had our nucleus, and around our nucleus was our electrons. But the big thing about Bohr was that he thought, okay, our electron can only be orbiting at very fixed radii away from the nucleus, right? So he thought the electron could be a certain distance away or a certain other distance away, right? So these radii differed with respect to they were farther from the nucleus than one another. But they could only be there, right? So they could only be in this radius or in this radius orbiting, and they couldn't be in between anywhere, okay? And so he had given these guys these like numbers, and we'll see what these numbers correlate to in a second. And the big idea behind Bohr was not, these guys weren't giving off light because they were orbiting. Instead, while we were seeing these emissions or these absorptions of light was due to transitions between these various radii, right? So if we had an electron in a higher radii fall down into a lower radius, right, then we would see emission of light of that essentially energy, right? And so whatever that difference in energy was between the two various radii, we would see that energy difference be emitted in a photon of light, right? And so this is why we were getting these emission spectrums. So Bohr himself could not quite explain why these electrons, because he imagined that they were orbiting the nucleus like the planets orbit the sun, why they weren't continuously giving off white light. So he called this like a peculiar mechanical stability that he couldn't quite explain. But again, this idea behind transitions between these orbits or between these various radiuses being responsible for these emission spectra was kind of big at the time, okay? So that's where we were left with. We still couldn't explain everything, okay? So now we're going to move on to this dude named Louis de Broglie, and he's going to give us kind of this idea that if we go back to this idea behind light, right? So light is majority of the time wave-like, right? It behaves like a wave. But when we look at energy, light has a very particle-like nature. So de Broglie took that idea and said, well, what if we turn that around on particles, right? So what if particles are particle-like, or electrons, that's the big one, not necessarily particles. So what if electrons, for the majority of the time, are particle-like? So particle-like. But maybe what if they also have wave-like properties as well? All right, so what if they behave like a wave as well? What if they have a wavelength to them? Okay, and so he kind of hypothesized this equation. This is called the de Broglie equation. And in this equation, what he said was the wavelength of an electron, or the wavelength of anything, really, is equal to h, which was, again, Planck's constant. So this is 6.626 times 10 to the minus 34th joule times seconds. So it's Planck's constant divided by m here is mass of whatever thing we're looking at, and then v here is velocity. Okay, so this isn't v, or this isn't nu. It's not nu. This is v for velocity. Okay. Again, nu is frequency, just to remind you. They look very similar. Okay, so that was the big thing, right? Okay, so maybe all things have wavelengths, right? Maybe all things behave like waves. The part in time, or the region of time, the region of space, or something like that, where this actually becomes important, like something having a wavelength, is when the wavelength itself is proportional to the size of the wavelength that it's representing. And I know that doesn't really make any sense, but if we take something like a baseball, right? So a baseball is really big, right? And so if we plug in all of the various parts of the baseball into this de Broglie equation, what we will get is a wavelength that's incredibly small. By small, I mean like 10 to the minus 34th, like meters, like really, really, really big, especially compared to the size of the thing that this wavelength is for, right? So because of that, the wave of the baseball doesn't actually play, you don't see it, like it's not there. It doesn't behave like a wave, right? Now, the only time that this wavelength actually starts to manifest itself in these various properties is when it's actually comparable to the size of the thing that it is a wavelength for, right? So, for example, an electron is itself incredibly small. So when you plug all of the various things into our equation here for the electron, we'll get wavelengths on the order of like 10 to the minus 10th, right? Which is actually very comparable to the size of the electron itself, okay? So things don't actually start behaving or manifesting their wave-like nature until they are actually on the order with respect to their actual wavelength, okay? Okay, so where would you actually need to use this de Broglie equation to calculate the wavelength? So let's say that we had a problem where I wanted to know the velocity of an electron that has a de Broglie wavelength of about 1.2 times 10 to the minus 10th. So how would I go about doing that? I would use my little de Broglie equation. So wavelength is equal to h over mass times velocity. And I would go ahead and solve for velocity here, because again, that's what we're looking for. So to do that, I would multiply both sides by mass times velocity. So that would give me mass, velocity, wavelength is equal to h. And then I would go ahead and divide both sides by mass times wavelength. And so that would give me velocity is equal to h over m times wavelength. And then I would go ahead and plug everything in. So 6.626 times 10 to the minus 34th. This is joule seconds all over the mass of the electron. This is like a constant. It's 9.1 times 10 to the minus 31 kilograms. And note you have to use kilograms here because, again, of joules. So 9.1 times 10 to the minus 31st kilograms times the wavelength of the electron, which is 1.2 times 10 to the minus 10th meters. Okay, so when you do that, you end up getting something like 6.1. Let's do that for real. Velocity is 6.1 times 10 to the 6th, and you end up in units of meters per second. So this is a point, 6 point. So when you look over here, you find, oh, look, here it is. So the electron is moving very, very, very fast. So things that are very small, moving very fast, have wavelengths that are comparable to the size of the actual thing. Okay, so that's great. So de Broglie can say, hey, what if all things have wavelengths correlating to them, right, corresponding to them? But how do we actually prove that, right? So how do we prove that the electron has a wave-like nature? It has a wavelength that manifests itself. So kind of proof of this idea, this wave-like nature of the electron, came a few years later in the following experiment. Okay, so right now, if you want a nice little video that kind of explains this better than I do, I would go ahead and stop this, and I would go to the Blackboard site and click on the video, the Dr. Quantum electron diffraction video, because that's going to explain this much better than what I can do right now. But I will try as well. Okay, so go do that. If you're not, then stick with me and I will explain exactly what happens in this experiment. Okay, so let's imagine we had a source of electrons, right? So we have some sort of electron source, and we are shooting them at a barrier, right? So we have a barrier here, and it has two tiny slits in it, right? And these two tiny slits are fairly close to one another, right? So again, the majority of the time we think of electrons being these tiny little particles, or like in the video they say tiny little marbles, right? And so if you take tiny little marbles and you shoot it at a barrier with two slits, what you would expect to see is the tiny little particles essentially coming through the slits where they're at, right, and landing right directly behind the slits on the screen behind them, right? You would expect particles to just go through wherever the slits were and end up right behind where the actual slits were on the barrier. Okay, again, that's what you would expect with electrons, which we think of as particles. What you actually get, though, with electrons is something different. So if you were to take an electron source and shoot electrons at a barrier with two slits, instead of getting the two, essentially two beams that correlate to the two slits, what you get is an interference pattern, which is very characteristic of a wave, right? Because waves diffract and they also interfere with one another. Okay, so this is a thing, like this is an issue. Like you're shooting particles at a barrier and you're getting an interference pattern. How could that possibly be? So scientists thought, well, maybe the electrons are going through and they're like diffracting off one another, right? And so we're getting this various thing. So they're like, okay, well, let's slow our electron source down so that it only shoots one electron at a time. And so they do that and they wait, right? Because if they're only shooting one electron at a time, it's only going to show up as one dot at a time on the slit, the photographic film behind, right, where they're actually seeing these guys end up. So they wait, and over time, as it passes, what they end up getting long term is, again, this interference pattern, right? So the problem with this is that you have an electron going one at a time. If you want to think of it as a particle, which people still want to think of it as a particle, you think, oh, it has to only be going through one slit. It can't be going through both, right? So that's the problem, right? How is it, if it's going through one slit, how does it make an interference pattern on the screen behind, okay? So, again, scientists wanted to figure out, well, it can't be going through both slits, right? So let's look and see which slit it's actually going through and see what we can make of that. So they do that, okay? And when they do that, they, again, have single electrons hitting the barrier one at a time, or going through the slits, and they see, oh, here's the electron, oh, here's the electron, right? So they're coming through, they actually see where they end up, but what that does is it essentially collapses the interference pattern, and it produces the type of pattern that you would expect just for particles going through the slit, right? So when you try to measure the position, or which slit the electrons are actually going through, the electron behaves like a particle, right? When you don't try to measure the position, when you don't know anything about the position of the electron, and instead just let it go through, then you get the interference pattern, which is part of its wave-like nature, okay? So this is kind of like the trade-off with respect to the electron, right? We've been asking this question, well, where is the electron at? What is it doing? How do we know? Well, in the end, what we can know about the electron is there are particle-like properties to it, and there are also wave-like properties to it. And it's going to behave as a particle or as a wave, depending on what you want to know about it, right? If you want to know where it's at, then it's going to behave like a particle, but you can't know anything about its wave-like nature. If you want to know the interference pattern it produces, right, then it's going to behave like a wave, but you can't know where it's at, okay? And that's kind of like where we come to, and what people have such problems with respect to quantum mechanics, is that there is no, like, you can't get better, right? You can't be like, oh, but we're going to trick it one day, and we're going to figure out where it's going and be able to measure the interference pattern. It's impossible, right? This is what essentially is told to us by the uncertainty principle, as well as the fact that these are complementary properties, right? The more you know about one, the less you can possibly know about the other, and that is what quantum mechanics really gives us with respect to the electron, which is unfortunate for some people. Okay, so again, these things were complementary properties. So this is a very particular term with respect to quantum mechanics. With complementary properties in quantum mechanics, again, the more you know about one, the less you can possibly know about the other, right? So with our little diffraction experiment, when we knew its position, we didn't get to see the interference pattern. But when we saw the interference pattern, we had no clue where the electron was actually at, okay? And so the wave nature, the particle nature, these are the two complementary properties, and their actual physical phenomena versus the interference pattern versus the position are what we mean by these properties, these complementary properties, okay? Okay, so this trade-off, this tit for tat with respect to these complementary properties are quantified or kind of formalized via what we call the Heisenberg uncertainty principle. Okay, so in the uncertainty principle, what they tell us is that position, which is part of the particle-like nature of the electron, and velocity, which is part of the wave-like nature of the electron, these are our two complementary properties that we deal with in the Heisenberg uncertainty principle, right? And so what it states is that the uncertainty in position, and that's what this delta x means, it's not change in, but instead is uncertainty. So uncertainty in position times the mass of the electron times the uncertainty in velocity. So this is uncertainty in velocity are greater than or equal to some finite number, right? And so what this is really telling you is the smaller the uncertainty in position, so the more we know about the position of the electron, the larger the uncertainty in velocity, so the less we can possibly know about its velocity, right? The more we know about the particle-like nature, the less we can know about its wave-like nature, and vice versa. And so again, these guys are kind of inversely proportional to one another. The more you know about one, the less you can know about the other. Again, the position of the electron is part of its particle-like nature, whereas the velocity of the electron is part of its wave-like nature. And that is what we're kind of left with. This is going to determine how we imagine these electrons, and not imagine them, but how we envision them occupying the region of the atom around the nucleus from here on out. Okay, so unfortunately, kind of the trade-off in all of this is that energy is essentially related to velocity, which is part of the wave-like nature of the electron. And we know lots and lots and lots about energies of electrons, and so kind of with respect to that, that means that we can't know very much about the position of the electron. Okay, so again, kinetic energy, which is what we're talking about, energies of this electron. This is related to the velocity of the electron via just the equation for kinetic energy. Velocity is part of the wave like nature of the electron. We know lots about these guys. We know lots about energies and velocities. And so because of that, we cannot know much about its position. And so unfortunately, that's what we're left with respect to quantum mechanics. So what does that mean? Okay, so this kind of leads us into the Schrodinger equation, which is developed or was developed by this guy named Erwin Schrodinger back at the, time that people were doing all this stuff. So what the Schrodinger equation does is it, for the first time, treats the electron as a wave, as purely a wave, okay? And so you don't need to know about this equation that much, right? The only thing you need to know is what we're going to get out of it, right? So what we're going to get out of this equation, let me start by saying what this equation is trying to state. So this part of the equation is essentially looking at the potential and kinetic energies of the electron, and it's equaling the total energy of the electron, okay? What this guy is, this little Greek letter psi, what this is what is called a wave function. Okay, so this is just like your normal functions like fx or something like that, right? These are normal functions, but with respect to the Schrodinger equation, these guys, these wave functions, are going to be our solutions to this equation, like solving for x or something like that. But with respect to this guy, we're going to get many different solutions. So many values of psi will actually satisfy this equation. Okay, so what's coming out of this is psi, and what this is trying to represent is the overall position of the electron. Okay, so position of the electron. Psi itself, all these different solving or all these different psis that we can get, has no physical meaning, but when we take psi and we square it, what this ends up being is the probability. So probability of finding the electron in a given region of space, okay, around the nucleus of the atom. So we're always going back to the atom. This is not just some lone electron living off in nowhere land, okay? Okay, so this guy, psi squared, again, we have many different possible solutions for this, and what we're going to call these are orbitals. So this is kind of a misnomer. It goes back to this idea behind the Bohr radius and like this electron orbiting. Again, it's just kind of stuck. So these psi squares, these probability distributions, we're going to call orbitals. Okay, so again, there are many different possible wave functions, many different possible solutions to the Schrodinger equation. The wave function itself has no physical meaning, but the wave function squared is going to give us our probability distribution of finding the electron in a given region of space around the nucleus, okay? So because there are many different solutions to psi, that means that we're going to have many different possible orbitals. All of these orbitals are going to be characterized by three separate quantum numbers, okay? So first one is what we call principal quantum number. The second is angular momentum quantum number, and the third is the magnetic quantum number. And it's going to be these combinations of what we call N, the principal quantum number, L, the angular momentum quantum number, and M sub L, right? So this is an M with a subscript L. These guys are going to characterize each individual orbital that we're talking about, okay? Each individual probability distribution of finding the electron in a given region of space. So right now, I know this has, you're like, what? I don't get it. It's okay. Hopefully I'll try to make sense as we actually start to deal with various values of N, L, and M sub L. Okay, so we're going to start by first talking about N, the principal quantum number, and what it is essentially going to specify about the orbital. Okay, so N, again, called the principal quantum number, what it is going to tell us about the orbital is it's going to give us the energy of the orbital, right? So overall energy of the orbital, as well as the overall size. And I don't mention this up here. So this will also give us an idea about the size of the orbital. Okay, so with all of these quantum numbers, they are all going to be integer values, right? So it has to be a 1, a 2, a 3, or 4 integer values, right? They're all going to have rules with respect to what number it can actually be. So for n, our rule is that n can be any integer greater or equal to 1, right? So n can equal 1, it can equal 2, it can equal 3, and so on. N cannot equal 0 or anything negative, right? So anything negative is forbidden with respect to n. So these guys do not count. So the only values that n can take on are 1, and then in theory, I think out to infinity or something like that, but we don't usually get out there. Okay, so again, that's the rule with respect to n, the values that it can take on. Number 2, another thing to note is that the larger the value of n, the more energy the orbital has. Also, the larger the value of n, the larger the orbital. Okay, so the bigger n, the more energy, the bigger n, the larger. Okay. And then one more thing. So what this n kind of represents, if we go back to the idea behind the Bohr model of the hydrogen atom, was those radii, those fixed radii, right? So instead of drawing them like Bohr did, what we're going to start to draw them more like is like this nice little energy diagram, as we have energy here on our y-axis, and we're increasing our principal quantum number here. These were essentially those Bohr radii. Okay, so n equal 1 was the one closest to the nucleus, n equal 2 was the next one out, and so on and so forth. So again, as n gets bigger, we're going to increase in energy, right? We're going to also increase in size. Also, as we increase n, what we're going to see is the energy spacing between the orbitals is going to get smaller, right? So for example, going from n equal 1 to n equal 2, we're going to get a certain energy spacing here. As we move up to n equal 3, that energy spacing between the two levels gets smaller, and it's going to continuously get smaller as we continue to move out, okay? So n can be any integer value from 1 to, I think, infinity. N tells you about the energy and the overall size of the orbital. The larger n, the bigger the orbital, the more energy, and then as we increase n, the difference or the distance between the orbitals is going to get smaller. The energy distance, I guess, between the orbitals is going to get smaller. Okay, so again, principal quantum number. Number 2, with respect to our quantum numbers, is the angular momentum quantum number. So we give the angular momentum quantum number this little denotation by the letter L. So what is L going to tell us? What is the angular momentum quantum number? So overall, what L gives you is the shape of the orbital. Okay, so each orbital is going to have its own characteristic probability distribution or shape, right? And so L is going to tell you what that shape is, essentially. So again, there are rules with respect to the values L can take on. So it can have integer values from 0 all the way up to n minus 1. Important to note here that L depends on n, right? So whatever n you have is going to tell you what values of L are possible. And then also important to note is that I think at the time people thought it would be confusing because, right, we're using n's with 1, 2, 3. If we were using L's, with 1, 2, 3, or whatever we're going to be using, so on and so forth, then when we talked about an orbital, we would call it the 1, 1 orbital or the 1, 2 orbital. So people thought that would be confusing, and rightly so, it would be confusing. And so because of that, each number for L is going to be essentially represented by a letter, okay? So, and I'll tell you which numbers represent which letters in a second. So there are, for us, in our intensive purposes, there are 4 orbitals or 4 letters that we need to know. So the first one is the s orbital, p orbital, d, and f. And these correlate to L values. So L values here of 0 for the s orbitals, 1 for the p, 2 for the d, and then 3 for the f's. Okay, so L. L gives you the shape, and then it depends on n, and it can have integer values from 0 all the way up to n minus 1. Okay, so let's actually do a problem that utilizes this. Okay, so for example, let's say we have an orbital, and that orbital has n equal to 4 as the principal quantum number. So what are the possible values of L? So remember that L can be any value from 0 all the way up to n minus 1, right? So L can be 0, it could be 1, it could be 2, and then if we have n minus 1 here, that's 4 minus 1, which gives us 3, so that is the last one that we can be, right? So L can be 0, 1, 2, 3, which is n minus 1. So there are 4 possible values for L when n is equal to 4. Okay, so again, with these letter values, or these number values, L equal to 0, this is our s orbital, our p, our d, our f. So this would be, correct answer here would be D, and this would be S, P, D, and F. Okay, so then the last one is the magnetic quantum number. So this is M sub L. So M with a little subscript L. So what does the magnetic quantum number tell us? So it's going to tell us our orientation in space, orientation of the orbital. And when we start to actually look at these orbitals, hopefully that will make a little bit more sense, right? So what are the possible values for M sub L? So M sub L can take on, again, integer values from minus L all the way up to plus L. This includes 0. So for example, if I had a L equal to 2, so again, an L equal to 2 correlates to the d orbitals, then my possible value for M sub L would be everything from minus 2, so minus 2, minus 1, 0, all the way up to plus 2, so plus 1, and then plus 2. Right, so integer values from minus L all the way up to plus L. So minus 2 all the way up to plus 2. And so again, M sub L is going to give us our orientation in space. That's not obvious from just listing these numbers. That makes very little sense. But what you should note is the values, the numbers of M sub L's that you get is going to tell you the number of orbitals present. So for example, for this L equal to 2, these d orbitals, there are 1, 2, 3, 4, 5. There are 5 values of M sub L. That tells you that there are 5 d orbitals. There are 5 separate, distinct d orbitals. And again, we'll show you that in a second. Okay, so let's try this question. So we want to know what possible values of M sub L are possible for L equal to 3. So again, go ahead and give this a shot and then push play again to get the answer. Okay, so we have an L equal to 3. Remember that our rules for M sub L are going to be all the way from, or integer values from minus L all the way up to plus L, right? And so for us, with L equal to 3, M sub L can be minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. Right, so correct answer here would be B. And so hopefully you guys went back, or you remember from a previous slide, when we had L equal to 3, L equal to 3 correlates with the F orbitals. Right, so this, again, just the number correlates with our letter here. And what this tells you, the number of possible F orbitals is given by M sub L. So there are 1, 2, 3, 4, 5, 6, 7 separate M sub L values, right? So that tells you that there are 7 F orbitals. Oops. Move this guy down. Okay. All right, so those are our quantum numbers. Okay, so all these guys are going to start coming together, right? So now we know these rules with respect to our N, our L, and our M sub L values, right? So again, L depends on N, M sub L depends on L, okay? So now, if we start thinking about our possible orbitals, and again, these guys are all specifying a distinct orbital, then depending on what n is going to depend on how many various orbitals there are, right? So for example, if we had n equal to 1, then the only possible value of L would be 0, and the only possible value of m sub L would be 0, right? So what this tells you is that when n is equal to 1, there is only a 1s orbital, and there is only one of them, right? Because there's only one value of m sub L, okay? So n equal to 1, we only get one orbital. It is the 1s orbital because, again, 0 for L is equal to s. That's what we denoted. Again, that's no like physical thing. That's just our notation. And so we will denote this orbital as the 1s orbital. And again, there's only one value. Okay, so now what happens when n is equal to 2? Right, so we increase our principal quantum number. So when n is equal to 2, now there are two possible values for L. All right, so L can be anything from 0 all the way up to n minus 1. So n minus 1 here is 1. So there are two values for L. So because of that, our m sub L's are going to have different values, right? So for L equal to 0, our possible value for m sub L would just be 0, right? So this correlates with the 2s orbital, right? And again, there's only one of them. Whereas for L equal to 1, our m sub L's are minus 1, 0, plus 1. So there are 1, 2, 3, and L equal to 1 correlates with P. So we would call these the two P orbitals, and there are 3 of them, because again, there are 3 separate values for m sub L. So as we increase the principal quantum number, we're going to start to increase the number of orbitals that are allowed, right? So if we move up to n equal to 3, now we have 3 possible values for m sub L, L, 0, 1, and 2, and then these guys all have different m sub L. So this would be 0, these guys would be minus 1, 0, plus 1, and then 2 would be minus 2, minus 1, 0, plus 1, plus 2, right? So what does this correlate to? So this guy would be the 3s orbital, and there would be only one of them. This guy would be the 3p orbitals, and there would be 3. And then this guy would be the 3d orbitals, and there would be 1, 2, 3, 4, 5. There'd be 5 of them, right? So when we denote these orbitals, we always put the principal quantum number first, and then whatever orbital or whatever value of L it is second. And we do that by the letter. Okay, so that's where the 3's are coming from. And then the letters are again coming from the various values for L that I'm looking at. Okay, so now some vocabulary with respect to this. So when we have orbitals that have the same value of n, they form what is called the same shell, the same electron shell. So for example, for our n equal to 1, there was only one orbital, and it formed its same electron shell, right? N equal to 2, though, had multiple different orbitals. It had a 2s and a 2p, and there were 3 of them, again, and so all of these guys were in the same electron shell. Now, if we have different orbital types within a shell, we call those different subshells, right? So what do we mean by orbital types? So if I move down to n equal to 2, or this is what we've been talking about, I have a 2s orbital, and then I have 3 2p's. These are different orbital types. That's what they mean by this. And so these guys, the 3 of these 3p's, they're in the same subshell, because there are 3 different orbitals that match this 2p, but the 2s and 2p, they're not within the same subshell. Okay, yeah, so again, just vocabulary, and that's not necessarily super important. This stuff, though, understanding this stuff is kind of important. Okay, so let's do a question. And so you'll probably see a very type of similar question. This is a very popular question on exams and quizzes, etc. So what I've given you here are 4 different sets of quantum numbers, and I want to know which one contains an error, which one is impossible given the rules that we have provided you for the orbital or the quantum number rules, okay? So again, one of these guys is incorrect, so I want you to be able to specify which one it is. So go ahead and stop this, think about it, and then come back for the answer. Okay, so which one is the correct answer here? So I think if we look at this, the correct answer is D. So for A, if we have an n equal to 3, then our possible values of L are 0, 1, and 2. And so that's fine. The L of 0 can exist. And then M sub L, if we can have all of these guys, then we can definitely have a 0. So that exists as well. For n equal to 2, so n equal to 2, our possible values of L are 0 and 1. So that matches. And then if L is equal to 1, then M sub L can be minus 1, 0, 1. So this one works out too. For n equal to 1, there's only one possible value for L, that is 0. And if L is 0, then there's only one possible value for M sub L, that is also 0. So C is good. So now what happens with respect to D? So if n is equal to 4, L can be 0, 1, 2, 3. So that fits. But now if L is equal to 1, then M sub L can only be minus 1, 0, and plus 1. Right? And so this M sub L, if L is 1, is not possible. Right? And so that's why D is the correct answer here. Okay, so now we've got these orbitals. We've got all these quantum numbers. We don't really know what we're actually trying to be specifying here, right? So again, these sets of quantum numbers, these n, L, and M sub L, are supposed to be specifying an orbital, all right? And we've already talked about these wave functions by themselves have no physical meaning. But when you take their square, what this is going to give us is a probability distribution of finding the electron in a given region of space around the nucleus, right? So now we're going to start looking at what these probability distributions actually look like. We're going to start seeing what these orbitals actually look like, okay? Okay, so the first one that we're going to start talking about is the s orbital. This is kind of the most basic orbital. And again, s is for L values equal to 0. Okay, so first way that we look at this, we're going to look in three-dimensional space, so x, y, z. This is what we are given here on the far left, okay? And what we see is what we're going to call a density of dots plot, right? So again, what we're plotting here is the probability, the psi squared, of finding the electron in a given region of space, and the nucleus here is going to be this 0, 0, 0 point of x, y, z, okay? All right, so what these dots are trying to represent is essentially the probability of finding an electron in that region of space, right? So, for example, let me actually go ahead and erase this guy. The way you can imagine this is that, let's say that we have our hydrogen atom, right? And we've got an electron in it, so that's great. And every 10 seconds, let's say we take a picture of where the electron is at, okay? So first 10 seconds, we take a picture, it's here, right? So we find one here, and then here, and then here, and then here, and then here, so on and so forth. We do that to like infinity, right? We overlay all of those pictures, okay? What we would produce is essentially this little distribution here. Okay, so where the dots are most plentiful or more dense, we have a much higher probability of finding the electron. Okay, when they start to spread out here, you have a much lower probability of finding the electron out in those regions. Okay, so if we go back to that idea of taking a picture and then overlaying them, we can kind of ideally, hopefully kind of hit another misconception that frequently occurs, right? So again, in my little idea here, I was taking a picture and then waiting 10 seconds, taking another picture, waiting 10 seconds, taking another picture, right? You would think that in that 10 seconds when I wasn't taking a picture, the electron was going from here to here and then here to here, right? But that, again, is a misconception, okay? So in reality, what happens in between these pictures is not that the electron is moving, but essentially the electron in between the pictures is a wave of all probabilities, right? So when we take the picture, we localize the electron to a specific position. So now we know its position. We can't know anything about its wave-like nature. When we don't localize it, when we don't take the picture, the electron is not a particle and instead is displaying its wave-like properties. So in between the pictures, it's not that it's moving from one spot to the next, it's instead a wave of probabilities of all of the regions of space. It's essentially like it's everywhere, right? Okay, so most people don't like that. So whatever, you take that however you want. Number 2, right? So this is the first way that we can imagine what these probabilities or these orbitals look like. Another way that we can kind of denote this, that we will frequently use, is what is called the contour model. Okay, so what the contour model is, it's essentially a surface, right? And for the s orbitals, these are always spheres. Spherically symmetric. What the surface is supposed to represent, though, is it's supposed to contain 90% of this density of dots plot, right? So they draw you a circle and they say 90% of this density of dots is within the circle that we have drawn, or the sphere that we have drawn, okay? Okay, so density of dots, probability distribution, probabilities of finding the electron in a given region of space. We can also denote this via these contour models, which again are supposed to be three-dimensional surfaces that contain 90% of our density of dots plot. Okay. Also note, really quickly, as we move from n equal to 1 to n equal to 2, what happens to the overall size of our contour model for the s orbital? It gets bigger, right? Which is what we would predict, knowing that the size of the orbital gets bigger as we increase n. Okay, so another way that we can kind of idealize these probabilities, another little graph that we can look at, if you will, is what is called the radial density plot. Okay, so the radial density plot is a little bit different than what we were looking at before. So what the radial density plot is trying to do is it's going out a certain distance from the nucleus, right? So let's say the nucleus is here. It's going to go out, and what it's going to do is it's going to essentially find the probability in that thin spherical shell that distance from the nucleus. And that's what it's going to plot on its little radial distribution plot, right? As we go out farther, we're going to get a little bit more of a shell, and we're going to be looking at a little bit more of a shell, but the density is going to decrease because, again, that's what happens as we move farther from the center, okay? So what we do here is we plot this, again, probability of finding the electron a given radius from the nucleus, okay? And that's what we get in these probability density or radial distribution plots. So note, with respect to all these plots, we do get a maximum probability, right? And so for hydrogen, this is 0.5 angstroms. This is our most probable distance that we will find the electron from the nucleus. And this actually ends up agreeing very well with experimentation. And with respect to the Bohr radius, this is fairly similar to what Bohr originally calculated in his model. Okay, so that's, okay, what does that mean? Who cares? Radial distribution or radial density function, we will come back to in a second. So don't forget about this guy. One other thing I wanted to note is what happens as we begin to increase in with respect to the s orbital, right? So for the 1s orbital, it is perfectly spherically symmetric, right? So it forms this nice perfect sphere. But when we go up to the 2s orbital, what we see is the introduction of what we will call a node, okay? So if we go back to the idea behind waves, right, and I can draw a nice little wave, a node represents the region where our wave crosses through 0. Right, so if we were imagining the electron as a wave, then again the node would be the same thing. It's where it would cross through 0. But if we were squaring a 0, we would also get a 0, right? And again, the square is supposed to be the probability. So with respect to nodes in these various types of orbitals, what that represents is a region of space that has 0 probability of the electron actually being, okay? And so the 1s orbital does not have a node. But when we go to the 2s orbital, we do see the first introduction of the first node, okay? So we do get a node. And again, that is a region of space where there is 0 probability of finding the electron, okay? As we move out to the 3s orbital, we see 2 separate nodes. Okay, so we can kind of follow that same thing. For the 4s, we would see 3. For the 5s, we would see 4. So it's always in -1 number of nodes that we are entering whenever we start to increase the principal quantum number. Okay, so radial distribution plot, most probable distance from the nucleus, and then as we increase n, we're going to increase the number of nodes, and a node is a region of space where there's absolutely zero probability of finding the electron. Okay, so those are the s orbitals. We can look at the p orbitals the exact same way. So for p, L was equal to 1, right? So this was our p orbital. And then for m sub L, we had -1, 0, and +1, okay? So now the p orbitals look like this, right? We call these dumbbell shapes. Dumbbell. I don't think that's how you spell dumbbell, but dumbbell shape, okay? So what you get is this nice dumbbell with a node directly at the nucleus, okay? So the p orbitals, even in their lowest energy or lowest principal quantum number, actually already have a node in them. Okay, so again, the L value, right, the angular momentum quantum number, that was always supposed to tell us the shape. And now it does, right? So for L equal to 0, that was our s orbitals. They were nice and spherically symmetric. Now for L equal to 1, these are our p orbitals. They are dumbbell shaped, and they all look this exact same shape, right? So now what was m sub L supposed to tell us? So this was supposed to tell us the orientation in space. So now we can demonstrate that with our p orbitals, right? So there are 3 of them. There are 3 2p orbitals, right? And the only way they differ from one another is which axis they lie along, right? What is their orientation in space? So we call the pz essentially is the p orbital that lies along the z-axis. The px is the same exact shape, but it lies along the x-axis. And then the py is, again, the exact same shape, but it lies along the y-axis. So these guys correlate with these different values of m sub L. So that's nice, right? That's what we told you. The orientation in space. That is what m sub L is supposed to be telling you. Okay, so we can continue to move out, right? So those were the p orbitals. There were 3 of them, and they only differed with respect to the axis they lied along. Now for d orbitals, this is a L equal to 2. So we had m sub L values of -2. I'm going to run into this, -1, 0, 1, and 2. So there's 1, 2, 3, 4, 5. These are the 5 d orbitals, right? Again, d, we call these kind of like clover leaf. They are all clover leaf shaped, right? Except for this odd one. This is a dumbbell with what is called a toroid. I don't think I'm spelling this right either. It's this donut around the center, okay? There's a special word for it. So they're all cloverleaf, and again, the only way they differ from one another is what axis they lie along, right? So the dyz lies in the yz plane, xz plane, xy plane, and then x squared minus y squared lies along the x and y actual axes, and this is dz squared, which is the weird shape, okay? What do you need to know about the d orbitals? Not much, right? Maybe know that they're cloverleaf shaped, because that's kind of neat. You need to know that there are 5 of them, but past that, you don't need to know much else about their various shapes or which axes they lie along or anything like that. And then finally, we come to the f orbitals. Okay, so L equal to 3 is our f orbitals. So possible values of m sub L are -3, -2, -1, 0, +1, +2, +3. So there's 1, 2, 3, 4, 5, 6, 7 f orbitals. And these are what they look like, right? So they're super strange, and most people don't deal with them all that much, okay? So what do you need to know about the f orbitals? There are 7 of them, and they're weird looking, right? So just, yeah, we'll leave that like that. Okay, so kind of spent a lot of time talking about these orbitals, and that's great, right? So now we have our little probabilities of where we can find the electron in a given region of space in an atom. How are we actually going to apply this, right? Where is this going? What are we going to do with all of this, okay? So again, the entire purpose of this was trying to explain the behavior of electrons in our atoms, okay? And when we put our electrons in our atoms, they are going to exist in these orbitals, okay? All right, so if we talk about hydrogen, right? So hydrogen, if we go back to the periodic table, has one proton in its nucleus. It has no neutrons. And then for the neutral hydrogen atom, it has one electron. So we are trying to figure out what this electron is doing, where it's at. So for all of these guys, all of these electrons are going to exist in what we call the ground state of the atom, which is going to be the lowest energy state, okay? And so because of that, for hydrogen, this electron is going to exist in the lowest principal quantum number in the lowest possible orbital, right? So for hydrogen, that would be n equal to 1. And so because of that, because there's only one type of orbital in the s, or in the one shell, then this would be in the 1s orbital. Okay, so the ground state for hydrogen, the one electron, is going to be the lowest energy orbital, which is the 1s orbital. And there's one electron in there, and so we can go ahead and write our little one electron. So this is what we call the electron configuration for hydrogen. There is one electron, which is what this superscript is trying to tell you, right? The one electron, and that one electron exists in this 1s orbital, okay? Okay, so what about the rest of the orbitals? Okay, so for hydrogen, what we find is, again, in the ground state, lowest energy state, our one electron goes in here. But for all of the other principal quantum levels, so n equal to 2, n equal to 3, what we find is all of these various orbitals, or all of these various subshells, these sublevels, all have the exact same, wow, that's interesting, all have the exact same energy as long as they're in the exact same principal quantum level, right? So, for example, the 2s for hydrogen and the 2p orbitals all have the exact same energy because they're all in the same shell. So this type of thing, where we have different orbitals with same energies, we call these orbitals degenerate. Degenerate means essentially same energy. Okay? Okay, so that's hydrogen. Great. We put the one electron in our 1s. That's where it exists. And so we move on, right? Okay, so now who do we move on to? What about helium? Right? So helium is next on the periodic table. It has 2 protons, right? It also has 2 neutrons, which we don't care about right now. But for the neutral atom of helium, we also have 2 electrons, okay? So now the question is, well, where do these electrons go, right? And so the problem with anything other than hydrogen is that the Schrodinger equation becomes too complicated to solve exactly, okay? So we can solve it for hydrogen, we get these solutions, we can plot these orbitals, so pretty, so nice. But when we move on to something like helium, or anything more than hydrogen, so there's lots of other elements, we cannot solve the Schrodinger equation exactly. And so what we are left with is what we call approximate orbitals. So we can approximate what they look like, and our approximations show that they tend to be very hydrogen-like. So we're going to continue to represent them via our same S, P, D, F ideas that we developed with hydrogen. Okay, so that's a problem, but we've solved it because we have approximations. Another thing that we have to consider is the effect of another electron, okay? And then another thing is what we call energy splitting of sublevels, and we'll talk about that later. So we're going to focus right now on another thing that we haven't talked about, which is electron spin. And again, the question, all we're trying to develop right here is figuring out, hey, helium has 2 electrons. Where do these 2 electrons go? Or they go in the s orbital, p orbital, etc. Okay, so spin. What is spin? With respect to the Schrodinger equation describes the orbitals, right? And it gives us the probabilities of the orbitals. And that gave us 3 separate values, n, l, m sub l, okay? There is a 4th quantum number, okay? That 4th quantum number is called m sub s, and what it refers to is the spin quantum number, or the electron spin. Okay, so where does this come from? So m sub s is a particular property of electrons. It does not come from the Schrodinger equation. It has nothing to do with the orbitals. Okay, and the way you can imagine electron spin is the following. So electrons are spinning. That's kind of how we imagine them. They are spinning like a top spins when it is essentially spun, right? When you spin a top, an electron is kind of spinning on an axis like that, okay? With respect to that, right, so we have this spinning particle, or spinning wave, whatever it is, right? If you have a charged particle, right, so a negative charged particle, that's what an electron is, that is spinning with respect to electricity and magnetism, anytime a charged particle is spinning, it produces a magnetic field. Okay, so because our electron is charged, it is spinning, it is producing a magnetic field. Okay, now the thing with the magnetic field is there are only two possible values to it, and it's kind of like imagining a north pole of a magnet and a south pole of a magnet, right? There are only two possible values. Okay, what we call this is first possible value, we call this spin up, right? So this would be spin up, and the second possible value would be spin down. So this would be spin down. The m sub s value is essentially referencing the spin up or the spin down, right? The magnetic field that this little electron produces. And so there are only two possible values. There are a value of plus 1/2, that's what we call spin up. And then there is a value of minus 1/2, which is what we call spin down. Okay. Okay, so because of that, again, this m sub s, the spin quantum number, not in the Schrodinger equation, but it is a particular property of electrons, and there are only two possible values. Okay, so again, we can represent these two possible values of m sub s as plus 1/2, minus 1/2. This is spin up versus spin down. Another way that we will frequently denote this spin is by using this little half arrow convention, right? So we will also represent our electrons as these little half arrows. So this is supposed to be our electron. And when we want to write it as spin up, we write this half arrow pointing up. So this is spin up, or a plus 1/2 for the m sub s value. If we want to write it as spin down, we will denote that as a half arrow pointing down. So this is spin down, and again, it has a value of minus 1/2. That's a 2, by the way. Okay, so different conventions for the exact same thing. So half arrow pointing up, spin up, m sub s is plus 1/2. Half arrow pointing down, spin down, and it's a minus 1/2. And so again, what this is supposed to represent are little magnetic fields, right? So if we take an electron with a spin up and we combine it in the same region of space with an electron with a spin down, essentially those two magnets will cancel one another. And this is what we call spin paired. Okay, so if they're not spin paired, they tend to have a little magnetic field. If they're spin paired, they will not have a magnetic field. They will essentially cancel one another. Okay, so what does this lead us to? All right, so when we're trying to talk about helium, again, with its two electrons, we want to know where that second electron is going to go. Where are these electrons going to go? We know that for hydrogen, the one electron went into the 1s orbital, right? So the question is, well, are both of these electrons going to go into the 1s orbital for helium, or what's going to happen, right? So this leads us into kind of an important little principle, which is called the Pauli Exclusion Principle. And what it states is that no two electrons in an atom can have the same set of 4 quantum numbers. Okay, so remember, N, L, and M sub L are going to describe the orbital. And so now the big question is, what are the possible values of M sub S? Because that is our 4th quantum number. There are only two possible values. There is a plus 1/2 and a minus 1/2. And so the N, L, and M sub L are going to tell us the orbital. If we can't have the exact same set of 4 quantum numbers, then the last little bit can only be two possible values. And so the big ramification behind this is that you cannot have more than 2 electrons in an orbital, and they have to have opposite spins. They have to be spin paired. So no more than 2 electrons in an orbital. Okay, so what does that mean with respect to helium? All right, so again, helium has 2 electrons. We're trying to figure out where those electrons go, right? For hydrogen, we know that the lowest energy orbital was the 1s orbital, right? So it had the ground state for hydrogen. And so now, what are the quantum numbers that actually define this orbital? So we thought about that. We would find that for the 1s orbital, it would be described by quantum numbers of n equal to 1, L equal to 0, and M sub L also equal to 0, right? So for the first electron that we want to put in, so electron number 1, it can go into our 1s orbital, which again are described by these guys. Now, one value for M sub S would be plus 1/2, and so we move on, right? So this is where the first electron goes. What about the second electron, right, for helium? So again, same orbital, 1s orbital, 1, 0, 0, but now we have a value of minus 1/2, right? So that's where they both go, right? So we have the 1s orbital, and there are 2 electrons in them. Now, if we said there's a third electron, right, and we tried to also put it into the 1s orbital, then we'd have 1, 0, 0, but then there are no other possible values for M sub S, right? So we'd have to repeat ourselves. But the Pauli Exclusion Principle tells us that we cannot do that. So no 2 electrons can have the same set of 4 quantum numbers. If I tried to repeat myself here, then I would have essentially just repeated the first electron, right? So we can't do that. And so again, big ramification for this guy is that there are only 2 electrons allowed in a specific orbital. So the electron configuration for helium is 1s, and now there are 2 electrons in that 1s orbital. So this is electron configuration. And then if we wanted to draw what is called an orbital diagram, where we write our orbitals as little boxes. So we have a little box here, and we would call this the 1s orbital. For helium, there are 2 electrons, so we would represent our spin up electron with our little half arrow up, and our spin down arrow with our little half arrow down, and these guys would be paired. Okay, so orbital diagram are these little boxes where we draw our electrons as arrows. Electron configuration is this little denotation here where we have our orbitals and how many electrons are in each one. Okay, yeah, so what happens as we move out with respect to the orbitals, right? So for the 1s orbital, there's only 1 orbital, so therefore we can have 2 electrons. For the p's, though, there are 3 orbitals. And since each orbital can hold 2 electrons, then the p sublevel can hold a maximum of 6 electrons. The d orbitals have 5, each can hold 2, so therefore it can hold a max of 10. And then for the s, or the f, there are 7, each can hold 2, so there's a max of 14 possible electrons in each of the various sub-levels. This is great stuff. Okay, so I'm going to stop here because I'm done talking about this for the day. Where we were at, and I just want to kind of remind you, is we were at helium, right? So we had just said, okay, with helium, where did that second electron go? Well, it went into the 1s orbital, so we had this beautiful little electron configuration. Now the question is, as we move past helium and we go to lithium, where is the now 3 electrons of lithium, where are they going to go, right? We know we can't put another electron into the s orbital because, again, we'd violate the Pauli Exclusion Principle. So the big question now is, where does this third electron go, right? First 2 are going to go into the 1s, so we're fine with that. But now the big question here is, do we put the third electron into the 2s orbitals, or do we put them into the 2p orbitals? Okay, so that's the big question, right? So I'm going to stop there, and we're going to solve that question next time. But just as a reminder, that's what we're trying to get at here.